All right, guys. So, lesson 6, we're going to talk about end behavior, and 6.6 is about end behavior. The end behavior tells us what is happening on the right end and on the left end of a function that we're going to be graphing, specifically a polynomial. Is it going in an upward direction or a downward direction? So that's what we refer to as the end behavior. Now, there is a type of mathematical notation that we're going to use to describe that, and it's something known as limit notation. So it's a new mathematical symbol that we're going to teach you guys how to use and write with. This is actually some stuff that you probably haven't seen before, and this is stuff that starts leaning in towards some calculus ideas. Limits are one of the foundational concepts of calculus. So you guys will get kind of a new idea given to you today, I think, unless you had a really cool Algebra 2 teacher that went over and above. Now, you guys don't have this slide, but I would just ask you guys to watch. So if I have this function here, suppose I want to plug in 0. What would I get if I plugged in 0? No. Undefined, because you would have 0 over 0. You can't have 0 on the bottom, and so this is undefined. Now, so what that means is that my function can't equal, my function has no y value for x equals 0, but we're going to see something interesting. Instead of letting my function have 0 plugged into it, we're going to approach 0 and see what y value we're getting close to. And that's what a limit is. A limit is where you're not finding what the function equals at a point, but rather what it's approaching at a point. Because sometimes you can't actually get there, like in this case. I can't actually get to the place where x equals 0. So let me demonstrate. What I'm going to do is I'm going to pick a number close to 0, like let's say 0.5. I'm going to plug that in. Now I've already done the math for that one. It comes out to be about 1.5. So I'm going to graph that point over there. You guys can see it as a red dot. Now I want to get another point that's close to 0, but maybe on the other side. How about at negative 0.5? I plug that in, I get 0.5, and I get that red dot. So right here we're at x equals 0.5 and x equals negative 0.5, but I want to get closer. So let's get closer. Let's pick something closer than 0.5. So suppose I were to plug in 0.25. I would get that y value, which would give me that dot. And if I plug in negative 0.25, that gives me that dot. So you can see they're kind of closing in on something. What does it look like it's closing in on? What y values look like it's closing in on? 2? Yes. We'll see. Let's get even closer than 0.25. So let's try 0.01. That's really close to 0. That's like 1/100th away from 0. If I plug that in, I get 1.01. And then if I plug in negative 0.01, I get 0.99. Okay, so you guys see how it's trying to close in on a y value of 1? Now remember, the y value doesn't equal anything there, but it's trying to get to 1. It just can't quite make it, okay, because it's undefined there. So as x approaches, down here it says a sentence, but you guys can't see it, but it says, as x approaches 0, y approaches 1. It can't equal 1, but it's approaching it. So in calculus, this is one of the most useful ideas there are, because there's these two big ideas in calculus called derivatives and integrals. Both of them come from an idea of, well, I can't actually equal that, but we can approach it. And so both of those ideas are based on limits. And that's like that's all of calculus, what I just told you. There's a lot to those ideas, but limits, integrals, and derivatives are all calculus. That's all it is. So this is like the heart of calculus here. It's the idea of, well, if my function can't equal something, what is it approaching? So even though the y value doesn't exist, it's trying to be 1. It just can't. All right? And so here is the notation that we use for that. Matter of fact, let me back up and I'll show you this. Instead of writing it out as a sentence, as x approaches 0, y approaches 1, here's how we would write that. We would write this word here, and we would write this. That indicates that x is approaching 0. Then we put the y value here. And then we say what the y value is approaching, which is 1. That's the notation that we would use to say as x approaches 0, y approaches 1. Okay? And that's called limit notation. So this little expression up here, I'm using f of x instead of y, but those are kind of the same thing if you want to write that in the notes there. F of x and y are the same thing. The expression above means that as x approaches c, the y value is approaching L. Okay, it's not about what it equals. It can be, but it's not about what it equals. It's about what it's approaching, what it's getting close to. Okay, so my main topic for today is end behavior. What happens at the end of your polynomials? Well, let's look at a parabola really quick. Where's the end of it at? Nowhere. You can't reach it, right? That arrow means it goes on forever. Can you reach forever? No, but can you approach forever? So we're talking limits there. So if I want to describe the end behavior, we have to do it with limits. And so that's how we'll be describing the end behavior of our functions today. So on this one, x is approaching infinity. This means x is approaching infinity. In other words, x is getting bigger and bigger and bigger. On a graph, what would that look like? Well, on a graph, where does x get bigger? Which direction does x get bigger in? To the right. So this is, I would like you guys on your notes to circle this and draw an arrow to that. So from now on today, when you guys see x is approaching infinity, I want you to understand that's talking about the right side of your graph. Okay? Now the answer is the y value. So let me give you guys a picture of a graph here. I'm going to circle the right side of this graph. What seems to be happening with the y? Is it going down or up over there on the right side? It's going down, and it's going down forever. So I'm going to put negative infinity here. So this means my graph is going down. So on the right side of my graph, it's going in a downward direction. That's what that means. As x approaches infinity, y approaches negative infinity. All right, let's take a look at another one here. Here, x is approaching negative infinity, which means that x is getting more and more and more negative. Which direction is that on? That's the left side of my graph. So once again, let's circle this, and we'll draw an arrow there to indicate. So when you guys see x is approaching negative infinity, we're talking about the left side of a graph. Now, let's look at the graph then, and let's look at the left side of the graph. What's going on with the y value? It's going up. And if I'm going up forever, what do you think I'm going to put there? Infinity. Okay, now, these answers that I put here are just for the graph that I put over there on the right side. You're going to see it's different for different graphs. But just wanted you guys to get the idea about what these mean. This is the right side. This is the left side. This side talks about whether you're going up or down. Okay? All right. Any questions thus far? So let's go ahead and look at our first example here. I kind of intended these to have arrows on them, so I'll put arrows on them now. They just didn't come out that way. Example 1 says, use limit notation to describe the end behavior of each function. All right, so I want to describe what's happening on this end and on the other end, both of those. But for now, I'm going to focus just on that guy. What side of the graph is that, left or right? So I'm going to put x is approaching infinity, positive infinity. Remember, positive infinity means the right side of your graph. All right, and then I'm going to label this graph as f of x. You guys probably should too, because I need to put something here, either a y or an f of x. All right, so what I've written here so far is I'm talking about the right side of my graph. Now what goes over here is what direction I'm going for the y value. Is the y value going up or down? Down, so I'm going to put what here? negative infinity. Okay? So if you want to add some little notes here to help you, you can. This means right. This means down. So the right side of my graph is going down is what that means. All right? So let's do another one here. Now, I want to do not just that side of my graph, I want to do the other side. So for that one, that's on the left. And if I'm on the left, then x is approaching what? Negative infinity, because the left is negative. And what's happening with the y value on that side? Going down again. So what am I going to put? Negative infinity. This time they're both negative infinity. That's different from the last slide, right? So this is just math notation for a really basic idea. This is just a fancy mathematical way of saying on the right we're going down, and this is just a really fancy way of saying on the left we're going down. Okay, but we want to get used to that notation. And also the reason for it, because you can't reach forever, so we use limits to talk about that, because limits are not what it equals, but what it's approaching. All right, so let's do the next one here. This time I'm going to ask for some help. Okay, Cole, I want to describe this arrow. So what goes here? You're close. You're right. You're close. One of these is negative if it's not that one. Let's call this one g of x, by the way. I forgot to put my g of x here. Why did you say negative infinity, Cole? Okay. So it's, what do you guys think? Why am I going to put, it's a positive infinity, so why am I going to put a positive there? It's on the right side. Okay, good. David, what am I going to put here? And why is that? Because going in a downward direction. All right. Next one, I'm going to ask Neve, what goes here? Good, and that's telling me about which side of the graph, Neve?
The other side.
More specific.
Oh, that one?
More specific.
Oh, the left.
There you go.
I didn't know you meant like.
Yeah, I got you. You're all right. Alvin, what goes after the equal sign there then? Huh? Positive infinity. Why is it infinity? Because it's going up. So remember, the ones under the word limit are talking about right and left. The other ones talking about up and down. All right, so student practice, of course. There you guys go. Give you a second. I'll ask you in a second what you got. We all happy with those? So we just used limit notation to describe the end behavior of functions as graphs. But now I'm going to give you, instead of a graph, I'm going to give you an equation. Okay? In other words, I'm going to show you guys how you can find the end behavior without looking at an actual graph. But before we do, we've got to talk about infinity a little bit. We're going to have to talk about infinity for a moment here. So, let's suppose that I had x times x. All right, so if I plug in 1, I get 1. You don't have to write this, you can just watch. If I plug in 10, I get 100. If I plug in 1,000, I get 1,000,000. So as this number here gets bigger and bigger and bigger, so does this one, right? So infinity times infinity, what do you think that's going to be? Infinity. Infinity. So that's one fact that I'll share with you guys. Now let me add a new fact in. Let's say that I multiplied this by a -2 now. What's the answer now? How about here? negative infinity. So basically it just changes the signs, right? I mean, yes, the number does get bigger because I multiplied by 2, but infinity is infinity, so you're not going to get bigger than that. But it does change the sign, so keep that in mind. So what do you guys think? Well, let's do this first. What's negative 1 times negative 1?
Positive one?
Yeah. How about negative 10 times negative 10? Okay, so you guys probably see where I'm going with this already. But I'm still going to keep up my process. So as that number gets more and more negative, the outcome's going to be what? Positive infinity. So it just follows the regular patterns for signs that numbers do. Infinity is not a number, but it does follow the same pattern there. Let me ask you guys this one. How about, what is negative infinity to the second power? It's infinity. And the reason for that is because that's just the same thing that I just had on the last slide, or the last exercise, right? It's just infinity, negative times itself. So you get positive. What if I had this? That's going to be negative, because when you do a negative times a negative times a negative, you get a negative, right? So those things are going to come in handy here. So what I'm about ready to do is I'm going to give you not a picture of a function, but I'm going to give you an equation of a function. Like, let's say f of x is equal to 5x squared. And our goal is I want to be able to tell what is the end behavior looking like. In other words, is it going up on the right or down on the right? Up on the left or down on the left? Just from looking at an equation without a graph. Why do you think so? Nice. Yep, you're jumping ahead there. So now I gave you this as a nice little reference, so let's fill it in together. The c represents a number. So a number times infinity is just going to be infinity. A number times negative infinity is just negative infinity. A negative times a positive infinity is going to be negative. Yep. And this one? Now, infinity raised to any power is just going to be infinity. But we talked about how if you have a negative infinity, and you raise that to an odd power, that'll be negative, yeah. But if you have a negative infinity raised to an even power, the negative goes away, right? So there you have it. So that'll come in handy for what we're about ready to do. Anybody still writing that? All right, so let's go ahead and proceed on to the next thing here. Okay, so complete each statement below and then sketch the right or left hand end behavior. So now I don't have a graph. But we're going to do this without a graph. So let me show you how we're going to do that. X is approaching infinity, right? First of all, what side of my graph am I thinking about right now? I'm looking at the right side. Now I want to know what's happening on the right. Is it going up or down? So to do that, I'm going to plug it into my function and see what I get. So we're going to plug infinity in for x. Now what is infinity raised to the fourth power? It's just infinity. Infinity raised to any power is just infinity. And what's infinity times a negative number? Negative infinity. So on the right side of my graph, it seems to be going down. So what we'll do is we'll draw a little picture here on the right side of the graph. And what we'll do is we'll show on the right side of the graph an arrow going in a downward direction like that. On the right side of my graph, it's going down. That's all that I know about that one. Let's go ahead and take a look at another one here. What side of the graph are we looking at for the second problem? What side of the graph are we looking at on the second problem? The left side. So we're going to plug that in now. And what's negative infinity to the third power? That's a negative. Anytime you have a negative infinity raised to an odd power, it stays negative. And a number times a negative infinity gives me. So apparently, on the left side of my graph, we're going down. So what would that picture look like? On the left side, we're going in a downward direction. Okay? So let's take a look at the next one here. I'm going to ask you guys to help me out with this one. So, Matthew, what side of the graph are we looking at for this next one here?
Right side.
Good. So we're looking at the right side. Glory, what am I plugging in for x this time? Infinity. And Evan, what is infinity to the 6th power? Yep. And then let me ask Caden, what's negative 3 times infinity?
Negative infinity.
Okay. So, Ruby, which way is the graph going on the right side? Down. So this graph would look something like this. It would look like the first one. On the right side, we're going in a downward direction. All right, let's do one more of these together, and then I'll let you guys practice a couple on your own. Annalise, what side of the graph are we looking at? Uh-huh. And Aswani, what am I replacing x with? Uh-huh. Good. And Gary, what is negative infinity to the 3rd power? Gary, what's negative infinity to the 3rd power? Okay. No problem. Michaela, what do you think? Negative infinity to the 3rd power. Huh? It's actually going to be negative, because if you think about it, 3rd power means it's negative infinity times negative infinity times negative. When you have 3 negatives, it always makes a negative as a result. So, negative infinity to the 3rd power is negative infinity. And we have a negative infinity. So, Rihanna, what's the final answer going to be? Good. And that means that Setis, which way is the graph going?
Graph is going to the right and up. No, to the left and up.
Okay, I like that. So here's what I want you guys to do for me. I'm going to draw a picture here. And I'm going to ask you to identify which one. I'm going to call on somebody, so don't shout it out. But I'm going to draw a graph here. And I'm going to put 4 different arrows. And we'll call this one A, B, C, and D. And I'm going to ask you, and I'll give you a second to think about it, but which one of those arrows is described by that last problem that we just did? All right. You ready?
Is it A?
Hannah?
No.
Huh?
B?
Yeah.
A.
Yeah, A is right. Left, it's left and up. That's this guy, left and up. All right. So, student practice. If you could do all that work mentally, you don't have to write out all the work. You can just put your final answer if you want to. But if you want to work it out, that's fine, like I did. But I do want you to also sketch the arrow somewhere next to it, all right? And then we'll move on. Cleo, fill in this blank for me here. Yeah, just the final answer. Very good. Let me ask Charity, what arrow goes with that one, that first one? Is it A, B, C, or G? The first one. No, I'm talking to Charity. What's your name? No. I don't think so. No. What do you think, Aiden? It's B. Right and up. That would be B. So I'll just put B there. You probably shouldn't put B on your paper unless you want to draw that diagram and label it also. Natalie, what goes in this blank?
Negative infinity?
No, positive infinity.
What?
Because when you cube a negative infinity, when you plug that in, you're going to cube it. It stays negative, and then you multiply a negative by a negative, and you end up with a positive. So now I'm going to ask Joelle, which arrow goes with that one? A, B, C, or D?
B.
It is A. Left and up. Left and up. All right. I'm out of cards, so for the rest, I'll just let you guys shout out what goes here. Negative infinity. Which arrow is that? C. Right and down is C. All right, next one. What is it? Negative infinity. And which one is that? D. That's left and down. All right. Now, you don't have to really worry about the last question too much, but I did see a couple people get it. So notice that this graph is going in a downward direction on both sides. Okay? So the coefficient must be, and the exponent must be, What do you guys think? There it is. Okay. So how did you get that? Is it just kind of like obvious, or do you have an explanation?
I mean, these are the first term in each of the functions. Yes, I went through the entire thing.
Okay. Yeah. What I've noticed is anytime the power is even, the arrows do the same thing on both sides. So either both up or both down. Another thing that I notice is that if they're odd, they're opposites. Okay, so that's one thing. The fact that it's going down would indicate that it's negative. That's kind of a harder question. I'm not going to ask you something like that on a test, but I just thought I'd talk about it. All right. Here. And we're going to pit two opponents against each other. In this corner over here, we're going to have x cubed. And in this corner down here, we're going to have 10x. And we want to know who the victor is going to be in the long run. Okay? So, let's take a look at round one. In round one, we're going to let x equal 1. So if I let x equal 1, what's x cubed going to be? 1. If I let x equal 1 here, 10. All right, so far, this guy's the winning. So we got x cubed, and we have 10x. So round 1 goes to 10x. Let's take a look at round 2. What's this one going to be? And this guy? All right, that's another victory for 10x there. Let's take a look at round 3.
That's 27.
27 and 30, right? Who's winning? 10x is still winning. That's pretty good. Let's take a look at 4. 64. And how about here? 40. Ooh, that's our first win for
Billy.
Our guy Billy over there. Yeah. What do you guys think is going to happen in the next
The
round?
rest of them is winning Billy.
So you think Billy's going to win from there on out,
Yeah.
right? And that's accurate, okay? So in the short run, this guy can have some effect on the outcome, but in the long run, this guy's more, pun intended, powerful. Powerful. Yeah. All right. So what I want you guys to say is, yes, in the beginning he can have some effect, but ultimately, at the end of the matter, this guy determines what happens. Okay? So let me put that away for a second. Let's talk about this. So a lot of times when I give you a polynomial, it's not just a single term like we were looking at in the last problems. Usually it's a bunch of terms put together. But let me ask you this. Who's the most powerful guy here? 7x to the 4th. This is the guy who's going to determine what happens to my function at the end. Whenever x gets bigger and bigger and bigger, this is the guy who's going to decide what direction that graph ends up going. This guy has an effect. This guy has an effect, and this guy has an effect. But ultimately, it's this guy who decides which way that graph's going to end up going because he's more powerful. Okay? So, That being said, we're going to ask the same question but with a different problem. So here we go. Example 3. Here's my function. I want to know what's happening on the right and left side of this function that we're talking about. Who really determines the end behavior of this function, though? This guy. That's the guy that matters. So if I want to find the end behavior of this function, then all I need to do is I need to find the end behavior of the most powerful term there. And then from there, we just do it like we've done before. So I'm going to go ahead and plug that in. And it looks like on the right side of my graph, we're going up. If you want to find the end behavior for this function, once again, all you need to do is you need to look at the most powerful term to decide that. This time I'll plug in negative infinity. Negative infinity to the 5th power is negative infinity. And 5 times negative infinity is negative infinity. So it seems like on the left side of my graph, we're going down. So on the right, we're going up, and on the left, we're going down. We could sketch a picture of that. On the right is up, on the left is down. And that's all we know. In later lessons, we're going to figure out what the rest of the graph looks like, but for now, we're just looking at the end behavior. Okay? So, review. How do you find the end behavior of a polynomial when there's more than just one term? Just do the work we've been doing all day, but with the biggest term, the most powerful term. Okay? All right, there's one for you guys. Once you're done with it, we're done, but keep your papers out because I will ask you guys what you got. So go ahead and knock this one out. And that will do it for today.